Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to depart from our usual format and answer some of the emails that I get. Once again, I have to apologize to you. I get hundreds of emails, and I don't have a chance to answer each and every one of them. So I'd like to, in the first part of Exploration, share with you some of my thoughts about some of the emails that I get. Well, let's just jump right into some of these questions that I get in the email. The first question concerns something ripped off right from the headlines, and that is the use of explosives to kill people. Well, we have incident after incident now where explosives are used to literally maim and kill people, and perhaps one day we'll have a way to detect them before they initiate their murderous spree. We had the recent incident in Nice in southern France where a man put guns and explosives inside a truck and then sent that truck right down the promenade, killing at least 84 people and injuring much more. And the question is, why don't we use our high-tech devices to scan for explosives? Well, once I had the pleasure of being at a luncheon where sitting next to me by chance was the former head of the Pentagon's DARPA program. DARPA is the agency which secretly investigates the kinds of high-tech devices and weaponry that go on to change world history. For example, one of the creations of DARPA was NASA. Yes, NASA itself was a byproduct recommended by DARPA, a branch of the Pentagon. Another device of DARPA was the Internet. Yes, back then it was called ARPANET. ARPANET was originally devised as a top-secret military weapon to communicate with our forces during and after a nuclear war. That's why the Internet has such peculiarities, such as no guideposts, no roadmap. The Internet is basically an empty road. Why? Because we scientists wanted it that way. We didn't want someone to say, can't use swear words on the Internet when we're trying to rebuild Los Angeles, rebuild New York City after a nuclear war. No, that's what we wanted. We wanted a clear highway with no road signs, no guideposts whatsoever. Well, now we're stuck with it because, of course, some people would prefer to have guideposts and a roadmap to the Internet. So that was one creation of DARPA. Another creation of DARPA was the GPS system. Yes, the GPS system was originally a military device, not so that hikers can locate themselves or mothers can find their children who are lost. No, the Internet was created to guide intercontinental ballistic missiles in outer space as they headed toward their targets in Russia. That's why the GPS was created, again, as a military weapon. So anyway, there I was sitting at this luncheon next to a former director of DARPA, and I asked him that very same question. I said, why do we have dogs sniffing for explosives at airports when we have all this high-tech wizardry with us today? And he said, well, look, let's look at what dogs can really do. Dogs live in a world of smells. If you were to somehow telepathically read the mind of a dog, you would not see necessarily images that are visual like we see. No, dogs live in a world of smells. Their olfactory nerves are many times more sensitive than ours. In fact, they're so sensitive, he said, that they can actually detect individual molecules. Individual molecules of explosives can, in fact, be detected by dogs. And that, he said, far exceeds our capability with sensors. Yes, he said, DARPA is not foolish. Yes, indeed, it tried to duplicate the olfactory nerves of a dog and failed. Mother Nature is still much more adept at identifying individual molecules than our latest sensors and our latest probes. So in other words, one of the safest ways we have still, the most efficient ways of detecting explosives is the old-fashioned way, and that is using dogs. And another question I get is, well, the Juno probe that zipped by Jupiter the other day got a lot of headlines, but hey, what's in it for me? I mean, if the Juno probe costs hundreds of millions of dollars, is a taxpayer going to get back their investment in the short term? Well, let's be blunt about this. In the short term, you are not going to get an immediate benefit. In other words, the short term, what's in it for me? The short answer is nothing. But in the long term, the state of technology and, in fact, the health of the Earth itself could be affected. In other words, the Juno probe in some sense is like an insurance policy. It's an insurance policy not just to create new technologies that are going to energize the economy, but an insurance policy because, well, let's face it, Jupiter is the 800-pound gorilla that determines the whole nature of the solar system. Why do we have impact craters at a certain rate? Why do we have comets? Why are they dangerous? And will one day one of them hit the Earth? Jupiter could be the key. In fact, without Jupiter, the Earth would have been hit millions of times in the past by gigantic comets and meteors. You see, Jupiter is a vacuum cleaner. It's a vacuum cleaner that cleaned out most of the dangerous meteors and comets, not all of them, of course, but many of them were cleaned out because Jupiter sucks them in or also flings them into outer space. So think of Jupiter as a gigantic snowplow. A snowplow that just plowed its way, eliminating much of the debris of the early solar system. So even though we have no immediate benefits from probes that go out to Jupiter, one day it could save our butts. Because we're talking about the fact that the universe, especially the solar system, is a dangerous place, that yes, the probability that a killer asteroid will one day hit the Earth is 100%. You wait long enough, and yes, it's a 100% chance that a killer asteroid or comet will hit the planet Earth. And to know more about them, we have to learn more about the 800-pound gorilla that determines the structure and the nature of the solar system itself. And that is the planet Jupiter. And another question that I sometimes get in the mail is, well, as you know, we're beginning to unlock the secrets of the brain. But what about dreams? Everybody dreams. We even think that animals dream. We go through a state called REM sleep, rapid eye movement. And rapid eye movement is very easily measured with our sensors on the brain. But if you look at REM of animals, you find, yes, dogs, cats, they also exhibit REM activity very similar to the activity of the human brain. So chances are they dream as well. And then the question is, why? What purpose? And why do we have nightmares? Well, now we have probes which can look into the living brain and seeing what's turned on and turned off. So when you dream, certain parts of the brain are shut down. That is, blood flow decreases, and it means that the cerebral cortex, the frontal cortex, the prefrontal cortex, is basically shut down when you dream. And the orbitofrontal cortex, which is your fact checker, which says, something's not quite right, something's wrong, that's also shut off. And that's why dreams are fantastic. The laws of nature, common sense, are suspended because the prefrontal cortex and the orbitofrontal cortex are basically denied blood. And so your mind wanders in all sorts of bizarre directions. And why do we have nightmares? Well, the amygdala, which controls emotions, especially bad emotions, that lights up. And other parts of the deep back of the brain are also lit up, meaning that you can sort of like walk and dream and move. And that's because the centers that control these activities are also lit up. So, in other words, your logic circuits are shut down. The amygdala, which controls nightmares as well as emotions, that's lit up. And the back of the brain, controlling crude physical activity of the body, for example, balance, that's also lit up. So you have the sensation that you're acting out the dream. And then the other question is, well, can you control a dream? And the answer is, in principle, yes. This is called lucid dreaming, which was once thought to be science fiction, but we now know is correct. At the Max Planck Institute in Germany, they did an experiment in Leipzig. They took a lucid dreamer who claims to control the nature of a dream, and they put him in an MRI machine. And sure enough, his prefrontal cortex was lit up even as he was dreaming. So in other words, he was fully conscious. All the conscious parts of his brain were fully awake even as he entered REM sleep. So in other words, he could actually control the direction of the dream. And in fact, the investigators asked him to clench his fist while he was dreaming because you are paralyzed while you are dreaming, but you are capable of clenching your fists. And so they could actually communicate with him, crudely speaking. Think about it. Talking to a man who is in a dream, and he talks back to you even though he is dreaming. Also, as I mentioned to you, you are paralyzed when you dream. In fact, I once had a lawyer on Exploration who has defended many sleepwalkers. In fact, there was one guy who actually killed his wife while he was dreaming. And his defense is that he's a chronic sleepwalker. And he was a scientist giving the science behind sleepwalking. So, first of all, when you dream, your motor centers are shut down and you are paralyzed. Because, after all, if you're not paralyzed, you can act out your dreams and all sorts of bad things can happen. That's what happens, for example, with sleepwalking. However, there are many recorded incidences of people that are fully asleep who do things like chopping wood, even driving a car. Think about that. Driving a car while you are asleep and chopping woods. Well, this gentleman claimed that he actually killed his wife in a dream. Now, this guy was not an ordinary person. It was chronic. He had a long history of acting out his dreams, even physically. And is it possible that he was dreaming and killed his wife? And the scientist says, yes, it doesn't mean he did it that way. But yes, it is fully possible that someone could actually kill somebody while they are dreaming. Now, this is also rather interesting because this also may affect the whole phenomenon called alien abduction syndrome. There are thousands, maybe even tens of thousands of individuals that claim that they have been abducted by aliens from outer space and taken to a flying saucer. And they very graphically explain that, yes, experiments, forbidden experiments on their sex organs were done while they were in this state. And, yes, they were taken in a flying saucer, kidnapped against their will. Well, who knows for sure? Perhaps it's true. Perhaps aliens do visit the Earth and routinely experiment on human beings. However, there's another possibility, and that is perhaps they suffered from sleep paralysis. Sleep paralysis affects 5-10% of the human race. In fact, in my astronomy class, sometimes I ask students how many of them have sleep paralysis, and about 5% of them raise their hand. And that is, when they wake up early in the morning, they have this dream that there is an animal, a gremlin, sitting on their chest, staring down at them, and they are terrified. They cannot move. They're paralyzed, because when you dream, of course, you are paralyzed, but they're still dreaming. The dream is still continued, and they think there's an animal sitting on their chest that is forcing them to be paralyzed. And then, of course, they wake up. Most of the time, they forget the dream, and they go about their daily affairs. However, sometimes, under hypnosis, they can recall the feeling of fear. And then on many occasions, the hypnotist says, well, if you have this feeling of fear and you're paralyzed, what is paralyzing you? Is someone holding you down? And then the person sometimes says, why? Why, yes. It now becomes clear. There are people holding me down. That's why I'm paralyzed. And then often, and this has been televised, in fact, often the hypnotist can then say, well, who are these people? Maybe they're strange. Maybe they're aliens. And then the person says, why? Why, yes. I see their faces now. They're not human. And it goes on and on. In other words, in this dream state, especially under hypnosis, you can be led by the hypnotist. And so again, I stress, I'm not saying that alien abduction is incorrect. Who knows? Perhaps people have been abducted by superior aliens with flying saucer technology. But there is another way to look at it. In fact, if you go back to the Victorian era, there are many paintings of sleep paralysis. That is, you have people that are still dreaming, but there's a gremlin sitting on their chest, staring down at them, even while they dream. In fact, you can Google it. Google these paintings of sleep paralysis painted during the Victorian era, and you find that, yes, it was rather common. A nightmare where you are dreaming while you are awake when you just wake up in the morning. And then the last question is, well, with all this technology, do we know why we dream? And the answer is rather embarrassing. The answer is no. There are many theories, but there's no consensus as to why we dream. We believe that animals dream. In fact, if you interrupt animals in their REM sleep, and do this continually so that it makes them incapable of undergoing REM sleep, some animals will actually die as a consequence. And so we think that, yes, dreaming is necessary, but why? Well, there are many theories. One theory actually coming from artificial intelligence theory. When you try to build a brain, a neural network of neurons that can learn, eventually this learning machine of transistors learns too much, and it goes into a dream state. A dream state where it tries to make sense of all the memories that it learned. And so there is a theory that says that all learning machines, all neural networks, including animals, maybe even including human beings, have to make sense of all the memories that come in. And just like cleaning out a file cabinet, they have to rearrange the files to make sense of these things. And maybe that's the reason why nightmares happen. Who knows for sure, but the amygdala controls memories, especially bad memories, and sometimes you have to relive them in order to make sense of them, to be able to file them away in a file cabinet rather than having them fester, because they are unpleasant dreams. And so there's one theory that says, coming from artificial intelligence theory, that perhaps there's a reason why we have nightmares, and that reason is because we want to make sense of this. We want to be able to file away these unpleasant memories, and that's why we have to relive them in some sense, and that's why we have dreams. Now, who knows for sure? But on exploration, we even had one of the world's leading authorities, a Harvard professor of psychology, who has written books about dreams, and in fact, he has cataloged thousands of dreams. He's taken thousands of young undergraduates in college, interviewed them, recorded their dreams, and he does find a similarity to many of these dreams. First of all, he says that there is a branch of psychology called the fortune cookie branch of psychology, which tries to say that maybe there are hidden meanings. Perhaps you can predict the future. He doesn't believe that at all. He simply says that dreams, for the most part, are random. Random, in other words, they connect different kinds of memories of the past, unpleasant memories, and sticks them together in illogical ways, because, of course, your logic centers are turned off. And that's the meaning of dreams. That is, dreams are not supernatural. Dreams don't predict the future. Dreams are essentially unpleasant, random thoughts that are then strung together at night, every night, in fact, when you dream. And then another question I get in email is the weather. Have you noticed that the weather seems to be strange lately? I mean, the news seems to be dominated by 100-year floods, 100-year droughts, 100-year heat spells, 100-year hurricanes, more and more disasters. Is there a way to show that, well, the weather is changing? Well, NASA had a press release just last week, and NASA satellites have verified the fact that the month of June last month was the hottest month ever recorded in the history of science. And then if you go back the last 14 months, we had a heat spell. You may not believe it because, of course, 14 months goes even through winter. But when you look at the planet Earth as a whole, not just the United States, but the planet Earth as a whole, and then you look at the weather, you find, yes, for the last 14 months, we have set yet another set of records that all the months of the past have documented a heat wave, the hottest 14-month period in the history of the Earth, topped by the month of June, which is the hottest month ever recorded in the history of science. And then if you look at average effects, not necessarily the ones that stand out as the hottest in 100 years, but if you take a look at the average effects, you see the effects that, yes, the Earth is changing. Every glacier, every major glacier on the planet Earth is receding. Pictures taken 50 or more years ago compared to satellite pictures taken today show a dramatic recession in all the glaciers. Not to mention the fact that we have the thawing out of the tundra near the Arctic Circle, large parts of Siberia, even Alaska are beginning to thaw out, and animals that were frozen tens of thousands of years ago are beginning to thaw out, freaking people when we see mammoth bones emerging in Siberia. But it's an indication not of luck on the part of anthropologists and biologists. It's the fact that the Arctic is heating up, releasing ice age carcasses that were frozen for tens of thousands of years. And so we know that, yes, the atmosphere really is changing. We also have the breakup of parts of Antarctica and the North Polar region. In fact, the North Polar region, in certain parts of the year, is melted completely. The North Pole is basically a puddle during the summer months, and we know that the average thickness of the North Polar ice sheet has decreased by 50% in the last 15 years. Not to mention the fact, talk to any farmer. Any farmer will tell you the weather's been changing. Every farmer will tell you that when he plants seeds for crops, the planting season has changed because summertime is roughly a week longer than before. So the seasons are beginning to change, and animals are adjusting to this new scenario. Animals have to adjust because, of course, their life cycle depends upon the seasonal changes, and the seasons themselves are beginning to change. Not to mention that mosquitoes bearing tropical diseases are moving north. As the Earth heats up, it means that normally mosquitoes that might be wiped out because of the cold months, they're surviving, and more pests are beginning to survive into the next season because they're not killed off during wintertime. So that is also changing. In other words, all the indicators, every single indicator indicates the fact that the Earth is definitely heating up on a scale not seen in centuries, perhaps even thousands of years. And then another question I get is, well, the Republican and the Democrats are at it again. Once again, it's, of course, convention season this week. And all the politicians talk about tax policy. Raise taxes, lower taxes, whatever. But you see, taxes do not generate wealth. Wealth ultimately comes from science. Now, politicians, of course, like to use tax in order to change the distribution of wealth. That can change, but the creation of wealth does not come from taxes. We've had three great technological revolutions that gave us enormous wealth. The first revolution was the Industrial Revolution, given to us by mechanics and by thermodynamics. And then in the 1900s, we had the electric age. We had the age of electricity, television, radio, microwaves, and then the third revolution is the high-tech revolution of today, giving us the Internet, giving us GPS, all the wonders of modern technology. The commonality of all these is they create wealth. Wealth generation because of science. However, the politicians don't understand this. They think that you can simply rearrange wealth and not create wealth. But you have to invest in wealth. You have to invest in science. You have to invest in science education. And that's something we have to continually stress. The world is not becoming less technological. It's becoming more technological. And people talk about the top 1%, but it's actually the top 30% that have done very well. The bottom two-thirds have either stagnated or held steady. And that more or less corresponds to the people that went to college. And they've done very well. And why is that? Because of technology. Because of automation. because of globalization, because of technology that infests every single branch of the economy. So in other words, education then becomes a primary foundation for wealth generation. We have to make sure that the people, especially the working class, are educated to handle this technology, because this technology is the third wave of wealth creation. And we have to make sure that workers are not left behind. In the second part of exploration, we're going to bring on a guest from MIT, Dr. Seth Lloyd, who believes that quantum computers will one day replace all the computers you see on laptops and communication systems and TV sets, all of that replaced by a new generation of supercomputers called quantum computers. In fact, he believes that the universe is a quantum computer of some sort. You know, we take computers pretty much for granted, and we assume that at Christmas time, computers are going to be roughly twice as powerful as they were the previous Christmas. But can that go on forever? That's called Moore's Law, and it's given us much of the benefits of modern-day technology. It's driven the economy. It makes our lives easier. It increases the reach of the Internet, realizing that billions of computations are done in a blink of an eye. However, Moore's Law can't go on forever. You see, right now in a Pentium chip, you can squeeze hundreds of millions of transistors. So each transistor in turn is roughly the size of a bacterium. And if this goes on, it means that eventually the computer chip will become the size of atoms, in which case the electron begins to leak out. And by the laws of quantum mechanics, the whole transistor circuit begins to fall apart. So in other words, we've made a transition from the early days of mechanical computing devices to vacuum tube technology, to transistor technology, to integrated circuit technology, and now to chip technology. Each time it set off a revolution. But the question is, what's next? Will eventually we be computing on atoms, in which case we'd have to go to a new generation of computers called quantum computers. By 2020 or so, we will gradually begin to exhaust the power of silicon because transistors will be so tiny that electrons will leak out of the silicon chip. And we need a replacement. And quantum computers may be it. However, even the CIA is interested in quantum computers. They are in principle so powerful that they could crack any computer code and you'll be able to eavesdrop on any conversation via a quantum computer. And Dr. Seth Lloyd also entertains the possibility that maybe the universe itself is one gigantic quantum computer. So once again, our special guest today is Dr. Seth Lloyd of MIT, and we're talking about the world beyond 2020. What happens when Silicon Valley becomes a rust belt, and we have to go to quantum computers. And now I'd like to introduce our special guest for today. We're very delighted to have with us Professor Seth Lloyd of MIT, author of a new controversial book called Programming the Universe. And the question is the universe a quantum computer? Now, let me explain. We all know that computers that energize modern society are based on silicon. And the silicon chip that you have in your Pentium crams literally millions upon millions of tiny transistors into something that's a little bit bigger than your thumbnail. And the question is, how far can you go until the tiniest transistor becomes the size of an atom? Well, that time is coming. Perhaps in 20, 30 years. We don't know precisely when. But we do know that someday transistors will be so tiny that atoms of silicon simply won't do. We'll have to go to atomic computers, otherwise known as quantum computers. And Professor Lloyd is an expert in this area called quantum computation. And he thinks maybe even the universe is a quantum computer. Now, let me also note that atoms spin like a spinning top. And you all know that spinning tops have an arrow, the axis of spin, and that could point up or down. If it points up, that's a 0. If it points down, that's a 1, and you get binary. But atoms are more than just binary. Atoms can also point sideways and anywhere in between, a superposition of up and down. And that's where we get into the bizarre world of the quantum theory, where you don't really know quite where this arrow is pointing, but you have much more freedom than simply zeros and ones. You have zeros and ones and in between. These are called qubits, or quantum bits. And Dr. Seth Lloyd is one of the world's experts in this new area. And of course, many people are interested in this. Modern technocrats are interested because one day quantum computers may have the internet on it, and as well as banking records and your credit card records, not to mention the fact that the CIA wants to get their handle on quantum computers, because with it, you can crack any code with a quantum computer. But you see, Dr. Lloyd goes even farther than that, because you see, everything around us is governed by atoms. Atoms, in turn, obey quantum mechanics, and therefore he claims that the universe is one gigantic quantum computer. And if that's true, then what is it computing? What's the program? Who wrote the software? God? I mean, your mind starts to go crazy thinking about the possibility that maybe the universe is a quantum computer. So once again, our special guest today is Dr. Seth Lloyd, author of the new book, Programming the Universe. Professor Lloyd, tell us a little bit about your youth. Were there any kinds of incidences or stories you'd like to tell about what set you off in a career in mathematics, computational physics, and physics?
Well, I always loved fooling around with numbers and with games and things involving geometry when I was a kid. I played a lot with blocks and would build huge geometric constructions as well as buildings with them. And then when I went to school, I was amazed to find out that there was a subject called physics where with relatively simple math you could discover a huge amount about the way the world worked. Of course, then I went to graduate school and found it was really the opposite. There's a huge amount of complicated math, and you only understand a little tiny bit about the way the world works. But by then it was too late. I was suckered into the field.
And you also mentioned in your book that as a graduate student, everyone seemed to be doing string theory, but you saw your destiny going in a slightly different direction. Could you elaborate?
Sure. When I was at Cambridge University, I did a MPhil in History and Philosophy of Science and started working on ideas of information and quantum mechanics. I also studied quantum gravity with Stephen Hawking. And it struck me that there was a connection between these two things, these two ideas of quantum information and quantum gravity. So when I went to Rockefeller University to work with Heinz Pickel to do a PhD in physics, I started off working on ideas of quantum information and quantum gravity, basically the same thing that I'm doing today. Unfortunately, they didn't like that very much at Rockefeller University, and about halfway through they told me I better cut it out and work on something more conventional like elementary particle physics or string theory.
Well, I guess reality intrudes. And Heinz Pagels, I should also mention, was one of the early guests on Exploration, speaking about elementary particle physics. Now let's talk about things that are very practical. The average American, of course, says, what's in it for me? Numero uno. Am I going to get better internet reception? Am I going to get better computer power? So let's talk about computer power, computer games, and what we have for Christmas. Everybody knows that at Christmas time, your computer is almost twice as powerful as the computers of the previous Christmas. And that's called Moore's Law. So some people say, well, Moore's Law is going to go on forever. However, you think otherwise. So tell us a little bit about Moore's Law and why you think Moore's Law is going to break down. So by Christmas time, we're not going to get Christmas presents that are almost twice as powerful as the previous Christmas.
Well, it's dangerous to predict that Moore's Law will break down. People have been predicting its imminent demise for decades, starting in the late 1960s. And every time some clever engineer managed to find a way around whatever specific problem seemed to be standing in the way of progress. And in fact, if you look at Moore's Law, it's not just one technology that has made computers get more powerful by a factor of 2 every year and a half or so. It's a whole series of technologies that have kicked in, from vacuum tubes to transistors, to integrated circuits. And these technologies rely on the rapid improvement of other kinds of methods like machining, material science, etc. So Moore's law is kind of the tip of the iceberg of this rapid improvement. However, it can't actually go on forever for a simple reason, that is that computers are governed by the laws of physics. And the laws of physics tell you how small you can make things and how fast you can do things. And so if you actually took all the energy in the universe and turned it into a gigantic computer, a possibility envisaged by Isaac Asimov in his story, The Last Question, I was able to calculate using the physics of information processing how big such a computer would be. And, this computer, this universal computer, if you like, up till now it could have performed about 10 to the 120 elementary operations, or ops, on about 10 to the 90 bits. And if you actually look at the exponential progress of Moore's law and ask at what point could the whole universe become a computer, it's only 250 or 400 years away. So even if we manage to take every elementary particle in the universe and turn it into have it participate in a computation, then Moore's law couldn't last for more than a few more centuries.
Okay, well, let's be very practical. On your desk is a laptop with a Pentium chip, let's say, and that Pentium chip has a layer of chemicals, the smallest layer being 20 atoms across. 20 atoms across, the smallest layer in a Pentium chip on your desk. In 20 years, in fact, less than 20 years, that layer will be 5 atoms across at the rate at which we're going. 5 atoms across. And at 5 atoms, we have to introduce something called the Heisenberg uncertainty principle, which says you don't really know precisely where that electron is. In which case, if electrons leak out of the layer, your Pentium chip just short-circuited, and your laptop is now useless. And so the question is, how small can you make a transistor before you bump up against atoms, and at the atomic level, everything's uncertain?
Yeah, well, that certainly is something to worry about. And indeed, if Intel starts making chips where the electrons are just leaking out all over the place, the chips wouldn't work. So they clearly can't make them by exactly the same design. However, there's certainly nothing wrong with, or nothing against the laws of physics to actually store bits of information at the atomic scale. Indeed, 1 atom, 1 bit. And as the components of computers get smaller, indeed, quantum effects like the Heisenberg uncertainty kick in. But maybe we can actually take advantage of these effects like the Heisenberg uncertainty principle. Maybe we can turn it from being a bug into a feature. And indeed, that's what my colleagues and I do when we try to build computers whose feature scale, the size of the bits, are down at the level of individual atoms.
Okay, now let's talk again very practical things when people say, what's in it for me? Well, the government, of course, would ask the same question, what's in it for us? And let's not talk about the CIA. The CIA, of course, is very much interested in breaking codes. They love to break the codes of other nations. But many times, to break a code, you have to have a key. And sometimes this key is the ability to factorize a huge number. Let's say I have a number with 100 digits. Take a sheet of paper and write a random set of integers 100 digits long, which fill up many, many sheets of paper. And then you are asked to factorize it as the product of 2 numbers. Well, how would you do that? It would exhaust most computers, and some people therefore think that certain codes are safe, that it's beyond the ability of most ordinary computers to crack the factorization of a number that's 100 digits long. But now, let's talk about computing on atoms. Is it possible that this new generation of computers, this quantum computers that you are pioneering, could be able to crack codes that even the CIA cannot crack?
Well, it's possible, and indeed, if we could build a quantum computer, a computer that stored bits of information on individual atoms, one with only a few tens of thousands of quantum bits, and one able to perform a few 100 million operations, which is to say something quite piddling compared with the laptop on my lap right now. If we could build a very small quantum computer, then we could use these kind of weird features like the Heisenberg uncertainty principle, to compute in a different way. And indeed, in 1984, Peter Shor, then at AT&T, now at MIT, showed that, in fact, you could exploit quantum weirdness to factor large numbers and break these codes with even a rather small quantum computer.
Okay, now let's talk about computers themselves. Everyone talks about the digital age. Everything is digital. But what does digital mean? And what is this zeros and ones that sometimes we see in the press? And like if you saw the movie The Matrix, you saw a bunch of zeros and ones. What are these zeros and ones? And what is the so-called digital age?
So a 0 or 1 is what's called a bit. A bit is the smallest possible chunk of information. And it doesn't have to be 0 and 1. The famous bits are yes or no, heads or tails, true or false, black or white. Essentially any thing that can take on two different states, two different distinguishable states registers a bit. And that's the smallest chunk of information. And the way that digital computers work is they break up information into bits, into its smallest chunks, and then process it that way.
Okay, so if modern society, the wealth of nations, everything we see around us, if it's governed by zeros and ones, then let's now talk about qubits, quantum bits, where atoms don't have to be in zeros and one states. They could be zeros and ones and in between. So tell us about how atoms can be in between 0 and 1.
Yeah, well, as soon as one starts talking about quantum mechanics, then things start to get weird. Niels Bohr famously said that anyone who can contemplate quantum mechanics without getting dizzy hasn't properly understood it. But let's go on anyway. Back essentially a little more than 100 years ago, physicists including Max Planck, Einstein, Niels Bohr, and others realized that there was an essential chunkiness to nature, a kind of a digital quality, that things that people thought of as being wave-like, like, for instance, light or sound, came in little chunks. Light came in little chunks called photons, a little particle of light. Sound came in little chunks called phonons, a little particle of sound. And so at this quantum level, things that look continuous actually are somewhat digital. For instance, you could have no photons in a spot or one photon in a spot. Or you could have one electron over here or one electron over there. And indeed, that's how a conventional computer registers this. So with a lot more electrons. So, bucket empty, lots of electrons out of the bucket, that's 0. Bucket full, lots of electrons in the bucket, that's 1. Now, in quantum mechanics, says, so at bottom the world has this digital feature, which is good because that means we can use this digital nature of the world, this quantum nature, to store digital information. But there's another weird feature of quantum mechanics that goes under the name wave-particle duality. So just as waves like light are made up of particles, so things like particles, like electrons, for instance, have waves associated with them. The wave is, an electron's wave tells you something about where the electron is. Now, so in a digital world, an ordinary bit, you could either have an electron here, that's 0, or there, that's 1. But in the quantum world, the electron's wave can be both here and there at the same time. So a quantum bit, electron here and there at the same time, is a bit that can register in some funky quantum sense that nobody really understands, 0 and 1 at the same time. Qubits are not either 0 or 1. They can be 0 and 1.
Okay, so let's take an analogy of a top, a spinning top. Everyone's played with them as children, and atoms spin, and therefore atoms are also like spinning tops, and atoms can spin either up or down when they're placed in a magnetic field, or at least until the quantum theory came in. And so now we can have tops that spin up, tops that spin down, and tops that spin in between. Now, these qubits, these quantum bits, can be between 0 and 1, and they consist of atoms now, not molecules of silicon that you see on a transistor. So how would you actually now build a quantum computer? Let's say that you were an inventor, have access to laser beams and magnetic fields and the ability to play with atoms, individual atoms, how would you build a quantum computer?
So, I guess, in fact, a little more than 10 years ago, I was in that position because quantum computers, the idea you could compute at the level of atoms using quantum mechanics, had been proposed by Paul Benioff and Richard Feynman back in the 1980s. But until by the early 1990s, nobody knew how to build one. Nobody had a clue. And around 1992, 1993, I realized that with off-the-shelf elements like lasers and microwave generators, you could take atoms and make them compute. And the way the type of computing I suggested was, in fact, just what you suggested. We'll take spin as our bit. So spinning up, or we can call that clockwise, is a 0, and spinning down is a 1, and then spinning sideways is this funky state of a qubit, 0 and 1 at the same time. So now, if you take such an atom, the spin of the nucleus of an atom, you put the atom in a magnetic field, and then you zap it with microwaves, you can make that bit flip. This is called magnetic resonance. It's the same technique that you use to image your knee when you blow it out while skiing. So if you put on light or microwave at just the right frequency, it will tickle the nucleus and cause the nucleus to flip. First it will start at, let's say, it starts at the state 0, or spin up, and then it gradually rotates down through the state spin 1 sideways, 0 and 1 at the same time, to the state spin down, or 1. Now if you have lots of atoms, lots of nuclei, you can address them with different frequencies. You can think, in fact, of these different atoms as essentially listening to different radio stations. So, if I have one atom that listens to 89.7 megahertz, WGBH here in Boston, then a second one, say the first one is carbon, say the second one is hydrogen, will listen to WCRB, 102.5. And when I address these two atoms with microwaves of different frequencies, or radio waves of different frequencies, then if I shine light at 89.7, the carbon atom, which listens to 89.7, will flip. And if I shine light or microwave at 102.5, then the hydrogen atom, which listens to WCRB, will flip. So I can address atoms individually, and then if you're sensitive to the interaction between the atoms, you can massage those interactions to make up logical operations. For instance, causing the hydrogen atom to flip if and only if the carbon atom is spin down or 1. And since at bottom, a computation is nothing more than making bits flip, and making one bit flip if another bit or several other bits, say, read 1, then any computation can be broken down into these simple operations, making bits flip, making them interact with each other. And the atoms in our molecule, the carbon and the hydrogen, can perform a simple computation simply by addressing them with light.
Okay, so let's back up a bit. You have a bunch of atoms, let's say in a line, and you place it in a magnetic field, so the spins are either up or down, or perhaps sideways, a mixture of up and down. And once you have these atoms aligned, then you hit it with microwaves, and at certain frequencies, the atom will absorb the radiation and flip.
That's right.
And each flipping process represents a calculation. Now, because the atom is neither up nor down, but a mixture of up and down, you have much more flexibility than in zeros and ones. Okay? Now, then the question is, what kind of computation can you perform on this? Can you do the calculations of a laptop? Can you do 1 + 1 is 2? What's the world's record for computing on these atoms?
So you can certainly take these atoms and make them do anything that an ordinary digital computer could do. So at the moment, because atoms are very small, and even if you extrapolate Moore's law into the future, depending on how you calculate size, then it will take 25 to 40 years for us to get computers where the components are atomic, even if Moore's law continues at a current breakneck pace. But the quantum computers we've built can do anything that a quantum computer, that an ordinary computer, say, with 7 to 10 bits can do, because that's the size of the computers we're looking at right now. However, so as viewed as classical computers, just doing ordinary operations like 1 + 1 = 2, then they're pretty weak, these quantum computers. Not only are they small in actual size, the size of of a small molecule, but they're small in terms of power. However, if we start to take advantage of the ability of atoms to read 0 and 1 at the same time, then quantum computers can do things that classical computers can't. And the secret comes from looking what bits can do in the computer. So bits can store data, but they also can be instructions. So 0 can mean do this, right? And 1 is an instruction meaning do that. Now, if I take a quantum bit, a qubit, that reads 0 and 1 at the same time, and I feed it into a quantum computer as an instruction, then the quantum computer will do this and it will do that at the same time. So quantum computers can multitask or do parallel computation in a way that classical computers can't. And that's why if we could build a quantum computer, say, with a few tens of thousands of quantum bits, which seems which is difficult, but certainly not impossible, then we might be able to start striking fear into the hearts of the CIA, the NSA, and other three-letter agencies.
Now, the reality, and correct me if I'm wrong, the reality is that the world's record for a quantum computation is, ta-da, drumbeat, 3 × 5 = 15. And I understand that calculation was done on something like 5 to 7 atoms. So correct me if I'm wrong, but at the present time, we're still at doing calculations that even children can do.
Tiny steps for tiny bits, Michio.
Mm-hmm.
You've got to start from somewhere. And indeed, as you pointed out, the whole notion that quantum effects might come into play strikes fear into the heart of Intel. So we have to figure out how to make atoms compute, and before we start to make Avogadro's number of atoms compute.
Well, I'm afraid that's it for exploration.